able to remember this. Okay, now just give me a thumbs up if audio video is fine. So can I just yeah, fine. So I'm just okay with this. Now as t tends to infinity, your amplitude should be finite. So it should be finite amplitude. Even if the amplitude is 0, as t tends to infinity is a finite, because 0 is a finite value. So this is what is called as bounded. If the input is having a finite value as t tends to infinity, then it is a bounded input. Even in case of output, if output has a finite value as t tends to infinity, then that output is also called as bounded. So what are the type of inputs which can be considered as bounded? So it is a delta function. It's a delta function is one of the bounded input. Assume that it is unit delta function. So this is having a magnitude 1. This is t equal to 0. So you can see this is my delta function, and as t tends to infinity, its value is 0. So it's a bounded input. Now what is other possible bounded input? Other possible bounded input is a step input. If it is of unit step, if it is of magnitude unit, you call it as a unit step input. So this is t equal to 0 it starts, and then it is constant with the magnitude 1. So as t tends to infinity, its value is 1, which is a finite value. It can be 1, it can be 2, it can be any value. So these two are considered as bounded inputs. Now let us consider some examples and try to see whether that system having a transfer function, is it stable or not. So let me consider a transfer function. When I say transfer function, let me say this as a closed loop transfer function. We know that this is input is RFS, this is CFS. Why I'm writing it as RFS? It is the Laplace of the input, it is Laplace of the output. It is now CFS by RFS, because that's what we define now. What is a transfer function of a system? Transfer function of a system is Laplace of output by Laplace of input. Assume that this system, let me just take a example of something like this. So that's what we saw now. This is assume that R is equal to 1 kilo ohm and C is equal to 1 microfarad, and we have a transfer function which is 1 over 1 plus SRC. If you substitute the values of R and C, you might have seen in one of the example, if it is this so and so, then I will have a transfer function which is equal to 1000 divided by 1000 plus S, or S plus 1000, correct? So my transfer function is 1000 divided by S plus 1000, correct? So this is my transfer function. Now if this is a transfer function, is this system stable? So where is the pole of this? The pole of this, as we know, is located at a position which is minus 1000. This is the S-plane representation of this pole, which is at minus 1000. Now to this signal, to this system, to this control system, if I apply a delta function of 1, a delta function with unit magnitude, what happens? So this is a delta function of unit magnitude, what happens? So let us see what is that. So what is this now? So what you have is CFS by RFS is equal to 1000 by S plus 1000, correct? This is what you have. If this is so and so, what you want to know, what is now, what is actually the C of t? What is the C of t? It is the input in time response. So this is the response. So now it is a time response. With respect to time is nothing but delta function, correct? If you have C of t, how do you find C of S? It is actually Laplace of delta of t. What is Laplace of delta of t? Only, of course, those who are learning control system should know Laplace transform and its Laplace inverse. So now I need to find, you can see now, if this is your delta t, if delta t is in domain t, in Laplace transform of delta function is 1. Laplace transform of the step input is 1 over s. Laplace transform of e power minus at is 1 over s plus a. Laplace transform of t is 1 over a square. I think all of you know these simple Laplace transforms in your mathematics classes. So that is so interesting or so important while doing the control system concept. So now let us know these Laplace. Now what we are supposed to do now, I need to find what is Laplace of this. So what is Laplace of this? It is equal to actually 1. So now what is CFS? CFS is equal to 1. So now we know what is Laplace of the input. Laplace of the input is, sorry, this is actually R of t, because extremely sorry for that, because R is input. So sorry, I don't care how it went back. So this is my input. So my input is delta t. Hope okay you get that correction. This is not C, is actually output. So what is R? R is an input. So input is a delta function. What is Laplace of the input? It is Laplace of that delta function, which is R of t. So what do you want now? I want to know for this transfer function, what is the output? So shall I write now CFS? What is this? This is Laplace of the output for this transfer function with this input. So shall I write it as R of s into 1000 by s plus 1000? Can I do this? Just give me a thumbs up. Can I write this? So I want to know what is the output for a transfer function of this for a given input, which is so and so. So just give me a thumbs up. So this is what exactly we are trying to do. We are trying to find out what is the output. What is the output if you know what is the input and what is the transfer function. So what is CFS now? CFS is equal to actually 1 into 1000 by s plus 1000. Correct? This is what you have. So now what do you want to know? You want to know what is the time response. What is this time response? What is time response C of t? It is nothing but Laplace inverse of CFS. Correct? Laplace inverse of CFS. So what is actually Laplace inverse of CFS? So what is CFS? It's actually 1000 by s plus 1000. Correct? Now this is my Laplace. So is this a constant? I'll take out this constant outside. What is Laplace inverse of 1 over s plus 1000? If you can see here, if you can see in this, what is, this is actually Laplace 1 plus SA, correct? 1 plus SA is the Laplace. What is its Laplace inverse? It is e power minus AT. So now can I write this? Okay, forget about this. So what is Laplace inverse of 1 over s plus a? Is this not e power minus at? Is it not? Is the Laplace inverse of 1 over s plus a, is it this? In place of a, what you have? In place of a, you have 1000. So can I now write C of t of this system having a transfer function for a input as delta function, is it not equal to 1000 e power minus 1000 t? Correct? This is my C of t? This is the C of t for a system having R and C with R is equal to 1K, with C is equal to 1 microfarad. The output what you are getting here, this is my CFS, is my output Laplace. C of t is output in time response. Is something like this. What does this actually mean now? So what is this? So where is the pole of this? The pole of this is there at minus 1000. So if there is a closed loop pole at -1000, what is the response of this system for a delta function which is a bounded input? Are you not getting? Is this something like this? So it is e power -1000t. Is it not actually like this? Is it not going this way? So this is when t is equal to 0. When t is equal to 0, this is e power 0 is 1. Is it not 1000? Is it not coming down like this? So this is your t. This is your t. As t tends to infinity, this will become. So what is this? This will become 0. This will become 0. So now it is tending to 0. What is this output? This output, is it a bounded output? As t is tending to 0, what is the magnitude? Magnitude is reaching 0, which is a finite value. So a system having a pole on the left hand side, will going to result in a system response which is a bounded output, So let us take one more example, which is simply like, okay, let us take something like, so CFS by RFS is 1 over, let us take simply an example which is S minus 1000. Let us take some example. So what is Laplace of it? So let us now take RFS is equal to 1, because R of t is a delta function. Because this is a bounded input, its Laplace is 1. So what is C of t now? It is Laplace inverse of 1 over S minus 1000. So what is S minus 1000? It is an indication of pole towards the right hand side, because this is S minus 1000. So what is Laplace inverse of this? Is it not e power minus 1000t plus 1000t? This is not e power minus at. So we know that Laplace inverse of S minus a is nothing but Laplace inverse of this is nothing but e power at. Can you see here? Just have a look at this. If this is S minus a, then this is e power at. This is e power at plus at. So what does that e power plus at indicate? So now what does this, how does the response of this look like? This is what is C of t. Now if you plot its time response, so assume that this is magnitude 1, it is 1 here at t is equal to 0. As t increases beyond 0, can you see the output is going like this? Output is keep going like this. So at t is equal to infinity, what is this magnitude? This magnitude is also infinite, which is not a finite value. So this type of output is unbounded. Correct? Why it is unbounded? Because as t tends to infinity, this output is not finite. So this is an unbounded output. So you have given a bounded input for a transfer function having it something like this, but output is unbounded. So a system having a transfer function like S minus 1000 is an unstable system. So this is CFS is bounded, but this is RFS. CFS is unbounded, because it is keep increasing like this. So what is the summary of this? Summary of this is, if a system has closed loop pole to the right hand side of the S-plane, system results in a unbounded output. If a system has a pole towards the left hand side of the S-plane, it results in a bounded output, which is a finite value as t tends to infinity. So system is said to be stable. So if it is this 1 plus S plus 1000, what is this is RFS, this is CFS. This is a stable system. Why it is stable system? Because its CFS for a bounded input is a finite value. As t tends to infinity. Just give me a thumbs up if you are all okay with this. So what is in two cases, when it is towards the left side, when it is towards the right side. So let us take up few more examples and try to see what happens if the poles are on the left hand side, but not only one, but many more. So let me just take an example where you have something like this. So now you take this. So it's not only one. So let us take a very general example. So you have a transfer function. So let us, for easier thing, we always take let R of S be 1, which means that you have an input voltage which is a delta function. Because delta function is a very commonly taken bounded input which results in a Laplace of 1, which results in Laplace of 1. So what is this now? If you have two poles to the left hand side, if R of S is 1, that is if R of t is equal to delta t, I want to know what is C of S and ultimately C of t. So what is this C of S by R of S? Now this is some general transfer function. If the transfer function of this is 1 over S plus 2, S plus 3. Can I factorize this? I can factorize this, and of course, can I write it as can I just write it as some A to S plus 2 plus some B into S plus 3 upon factorization? I can do this. So this is what is into RFS. But what is RFS? RFS is 1, so this remains the same. So what is CFS now? CFS is, or what is C of t? It is Laplace inverse of A S plus 2 plus of B S plus 3. So this A and B is some value. So what is the Laplace inverse of this? What is the Laplace inverse of this? Laplace inverse of this is A e power minus 2t. This is B e power minus 3t. So being a control system engineer, I'm not too much worried about this A and B. I'm worried about whether this is minus or plus. Because what is the time response of this? Because where are the poles now? The poles are there at minus 2 and minus 3. This is my S plane. This is my S plane. What is the time response of this? The time response of this is it starts at A and it comes down. Correct? What is this? So this is having a time response. So its magnitude is 3. Since it is e power minus 3t, it decays faster. It decays faster than this. Suppose if I relatively write these two, if this is at A, if it just goes like this, the one which is there bit far away. So let me just write it for this. So it will go a bit faster. See here, decaying is faster when this is more. Correct? Suppose instead of minus 3, if it was 30, so it would have decayed faster. Now, what is the overall response? Overall response is this plus this. So this plus this is the overall response. This is what is the response. So what is the overall response? Overall response will be something like this. But is this a finite value as t tends to infinity? Yes, it is a finite value. So now a system having two poles onto the left hand side is also a stable system. Is that fine? So just give me a thumbs up if you have two poles onto the left hand side. So we saw with only one. When only one was there, it was certainly stable. Now we consider two. For two also it is response of first and the second one. So they are actually stable. So system is giving a finite value as t tends to infinity. And let us do the same. Let me add one more term which is s minus 1 to the same. So let me have this. So now you have a pole to the right hand side. So does this become some s minus 1, and will it have some c s minus 1? So will it also have some c s minus 1? These ABCs are totally different. But what is the Laplace of this? Is it not c e power 1t? Because this s minus 1 will result in e power t. So when it is e power t, you have the response of this something like this. The response of this is so and so. The response of this would be something like this. If you add this plus this plus this, what is the result? It is this plus this plus this. What is the resultant? The resultant is this. The resultant is this. So what is this system? Even though you had two poles onto the left hand side, since one of them is there on the right hand side, system will have a infinite output as t tends to infinity. So we have to have all the closed loop poles should be onto the left hand side, even if one goes to right hand side, because the overall response is the addition of all the responses. It's like having 0.01 plus 1000. So is this 1000 is more or this is more? Even though you have n number, so this 1000 will become infinity as t tends to infinity. So then naturally the system will become unstable. The system will have an unbounded output. So system will become unstable. Getting now? It is not how many poles you have to the left side. You have to see how many are there to the right side. Even though you have hundreds of poles on to left side, if one goes to right hand side, entire thing is unstable. It's like an AND gate. In an AND gate, if it's an n bit n input AND gate, if one of the input becomes 0, output is 0. No matter all these inputs are maintained as 1, since one of them is 0, the entire output is 0. Exactly here. When all the inputs are on, when all the poles are there on the left hand side, system is stable. If one goes to right hand side, then entire effort of all these poles will be get spoiled. So that's what is the entire concept of control system lies in finding out, is there any closed loop pole to the right hand side of the S-plane. That is the entire story behind this. Is that fine? Will you just accept that this is what is that you're looking for? We are actually looking for, is the pole is there to the left or right? If one goes to right hand side, system is unstable. Why? Means it is just the addition. Am I clear with that message? Any thumbs up, or do you want any more of course this is very pretty clear. So you just add that, so it is so and so, just add all of them. If one of them becomes onto right hand side, it's like e power t, and there are so many e power minus t's, so it is just hardly, it doesn't matter how many are there to the left. If one goes to right, the entire thing is collapsed. Now we have seen the poles on the real axis. Let us see, if you have a pole on the which is complex, what happens if a system is having poles which are like complex. So that's what we saw now, plus or minus so and so. Assume that I have a pole, I have a system which is something like 1 over s plus 2 plus or minus j3. Where are poles now? Poles are here. This is minus 2, this is a reference. This is plus j3, this is minus j3. Their intersection is here, so you have a pole here. You have a pole here, correct? So this is just a marking point. This is just a marking point. Their intersection is happening here. I have a pole here. I have a pole. So what is the pole position? Minus 2 plus j3. This is minus 2 minus j3. Correct? So this is what we are looking at. So it is s plus 2 plus or minus j3. So now what is the transfer function? You have a transfer function. C of s is equal to R of s into 1 over s plus 2 plus j3, and let me just write it as some a. This is b upon partial fraction. This is s plus 2 minus j3. What is Laplace inverse of 1 over s plus a plus jb? So what is, just have a look at this. So this is one of, see here, what is that you have? Something like this. This is you have suppose if you have something like this, if you have a complex term, of course this can be further written as so on. So this results in this entire thing. Suppose now I can write this as, so this can be written as, so if you have a pole which is at complex, what will happen to this is this will end up with e power minus at and sine omega bt. Okay, sine bt. Now what is, it will going to have a decayed response, but in the decayed response there will be some oscillations. That oscillations will be in the frequency of b. So now what will be this? So this is e power minus 2t sine 3t. So what is the response of this? Of course these two will have a response something like this. So it is having a decayed response, but this decayed response, this is what is the magnitude, and the response would be like this. So you have a oscillatory response, because of these two, but that response is decaying. Meaning if you have a complex pole, you will have a oscillatory response, but amplitude is decaying exponentially at a rate depending on where is the real axis is. Suppose if it is too far away, assume that this is at minus 20. So then it decays faster. So now what does this mean to say? Since the poles are there onto the left hand side, you have an oscillatory response, but it is decaying. Is it bounded? Yes, it is bounded, because as t tends to infinity, this magnitude becomes 0. Now similarly take this onto right hand side. If a pole comes to right hand side, a complex pole, then what is the response? Response is still oscillatory, but it is exponentially increasing. Can you see here? It's increasing. So as t tends to infinity, this is also going to infinite, because you have a e power 2t sine 3t. Why this is 2t here? Because this is negative. Why this is negative? This is negative indicates there is a pole to the right hand side of the plane. This is at 2 and this is at again plus j3 and minus j3. So this results in a oscillatory response which is keep increasing. So if a system lies to the right hand, if the closed loop poles of a system lies to the right hand side of the S-plane, system is again unstable because it is giving an unbounded output. If it is there on the real axis, it was decaying slowly. It was decaying like this. Now it is not simply increasing, the oscillation amplitude is keep increasing. Because they are complex in nature. Suppose if you have a system something like this, what happens? Now these are all varieties. If you have 1 over S as a system, if this is the system, so now CFS is nothing but R of S into 1 over S. So what is R of S? It is 1 into 1 over S. So what is this C of T? C of T is Laplace inverse of 1 over S, which is nothing but 1. So if we have a pole at the origin, because we know that if it is there onto the left hand side, it is decaying. If it is there onto the right hand side, it is increasing. So it is unstable, stable. If it is there on the origin, something like this, what is the system stability? You can see if for such a system, if we give a bounded input with the delta function, output is a DC value of magnitude 1. Correct? So this is, if you have a system with closed loop pole at the origin having this type of transfer function, this is a stable system. Correct? Why it is stable? Because output is constant. Output is a finite value even if t tends to infinity. Suppose even if t is equal to infinite, what the magnitude? It is 1. Is it fine? So we are looking at what happens if the pole is there right on the origin, right on the origin. If it's on the origin, it is perfectly a DC response, system is stable. Now, if it is this, you are having repeated poles. You are having repeated poles. If it is repeated poles, shall I write it as 1 over a square, 1 over a square. What is Laplace inverse of 1 over a square? Just go back here. See here. What we have? We have, can you see this? This is 1 over a square. This is Laplace of t. What is Laplace inverse of 1 over a square? It is t. So now, what is Laplace inverse of 1 over a square? It is now t. So what is the response of this? For a delta function, the response is like this. It's a ramp output. So this is your C of t. So as t tends to infinity, what is its value? This value is also infinity. So what is system? System is unstable. So this system is unstable. A system having repeated poles at the origin is unstable, whereas if you have only one pole at the origin, then it is stable. Then it is stable. So that's why we are so much interested in finding where the poles are. We're just looking at what happens to your pole position if it is, suppose if it is keep changing, suppose the pole position keep on changing, what is the system stability? So that's why in the previous class we were so much worried that if the system has got poles onto the left hand side, system is said to be stable. If it is there onto the right hand side, system is called as unstable system. Special cases, if you have only one pole at the system, stable. If you have repeated poles at the origin, it is unstable. Now the question is, if you have complex pole, suppose if the poles are on the imagined axis, supposing that you have 1 over s plus j3 and s minus j3. This will result in 1 over s square minus 3 square, which is nothing but you have poles on the imagined axis. Laplace inverse of this is sine 3t. What is sine 3t? You might have seen that here. Can you see here? What is the response of this? If we just go back here, sorry, it is s square plus. So this is what you're going to have. So this is what, okay, it will be s square plus 3 square. The roots are so and so. Okay, this may be root 3. Okay, forget about that. So if you have complex, suppose if you have poles on the imaginary axis only, there is no real part is 0. In such case, what is its Laplace inverse? Its Laplace inverse is sine. Its Laplace inverse is sine. Meaning, if you have poles on the imaginary axis, it results in an oscillatory system. We talked about 3 systems now: stable, unstable, and oscillatory. Now, shall we just go back and see when does a system is stable? A system is stable if all the poles are there onto the left hand side of the S-plane. When it is unstable, even if one pole goes to the right hand side of the side of the S-plane, system is unstable. When the system is oscillatory, if the poles are on the imaginary axis of the S-plane, then we call it as system is oscillatory. So this is what is 3 different ways of representation of stability of the system. So now the entire control system, in various topics we talk about where the poles are. This is the entire story behind the control system. Is the poles closer to stability, how much it is away from that, all those stuff. Now, So as I said, okay, now let us consider the time response of a system. So we talk about whenever you consider any system for that matter. So this is a system. So once you know the transfer function of the system, why a particular system, what is the use of that particular system? So you'll be applying some input. I want to see what's its output. So now it's with respect to time. So when you are looking something with respect to time, that is called as time response. Time response of a system. Time response of a system. And we know that this is with respect to time. Whatever signal that you're applying, suppose if it's a sine wave. So if it's a sine wave, there's a time related. So when you say a sine wave, it will going to have some amplitude, it will going to have some frequency. So it's not only the time, so this frequency can be different. So this frequency can be 100 hertz, it can be 1 kilohertz, it can be 100 gigahertz, it can be any frequency. Now, along with knowing how it behaves with respect to time, I should know how does this system behaves for different frequencies of the input signal. Then comes frequency response. So that's why for any system, we should know what is the time response of the system, because all real-time responses are with respect to time. After applying this, how it behaves. That is what is time response. Along with that, I should know if I change the frequency of the signal, what is the response. So that is captured in frequency response of the system. Frequency response of the system. So now we know that we should know the time response of the system. So now when you are having time response of a system, so now what is this system? System is represented by a transfer function. So when system is represented by a transfer function, it will have n number of poles and zeros. So let me consider you have let us take it as 1 over s plus 1000, correct? So how many poles are there? You have only one pole. So what is the response of this? We saw the response of that is keep going down like this. So it is decaying. Suppose if it becomes 10,000, it decays faster. If it becomes 100, it decays slowly. If it becomes 1, it decays very slowly. If it is 0, it's a perfect DC. Correct? You can see now the pole position matters for the response. If you have only one pole, it is this. If you have two poles, if you have three poles, if you have four poles, usually the number of poles in a system can be n. So now when you say you have n number of systems, let us take this is the system what you have. You have n number of poles, and you have few poles which are there here. So what is the number of poles you have? You have so many numbers. Now shall we start writing its response? So assume that this is a pair. So can you see it is going to have an oscillatory response, and then it is keep coming down because it is too far away and the decaying is fast. So now here it's a different imaginary value, different real value. This is got a different real value. So they are it's like a response of this plus this plus this plus this plus this. All these are added and the overall response. And you can see these are the two response which are the closest to the imagined axis. So when it is closest, we know that whenever it is closer to this will have e power minus t. This will be least. So now, even though we have these many poles, it's like in a team of 11, members, all the members are important. It's like having Kohli in the team. If Kohli plays, we know that we're going to win, meaning that he is an important player. He is a dominant player who will decide the fate of the team, whether it's going to win or lose. I'm just giving a very loose example. Now we are looking at in any particular thing, so there will be some key people who can able to contribute to the stability of that particular team. So in this system, we have so many poles, out of which whose response is more deciding one. So now in a control system, even if you have n number of poles, the poles which are closer to imaginary axis will dominate the response. So we call those poles which will dominate the response as dominant poles. This is dominant poles. Even though you may be having n number of poles, but dominant poles are only 2. So now when you want, because of course assume that okay, if these poles contribution are negligible, I will not consider that, even though that is important, but the contribution of this pole response is very important compared to all this. It's like having e power minus 100t plus e power minus 300t and e power minus 400t and sine 10t and e power minus 3t. So, and assume that you have plus e power minus 1 sine 100t. Out of this, which one is, does each one of them is contributing to the response, because it is this plus this plus this plus this plus this. Out of all of them, which is more contributing to the output finally? You can see this. So you have a response of each one of the poles and zeros on the poles onto the left hand side. The most dominating is which is there towards the imaginary axis. So I will call this response is more dominant than all other things. So you try worry about what is the response of this system. So in finding the time response of a system, even though the system has n number of poles. So suppose if you have a pole, if you have s plus 10, so I'll call it as first order system. This is a first order system because number of poles is 1. Suppose if you have s plus 4, so this will become a second order system. Now assume that you have s plus 6, so this will become a third order system. Assume that you have s square, now it is 2 plus 3 plus 4 plus 5, so it's a fifth order system. Suppose if we have s plus 10 and s plus 12, so it is seventh order system. So order of the system is keep increasing. So when order of the system keep increases, you are not supposed to worry about what is the time response of such a highest order system. Out of this, only 2 poles will be dominating. So while finding the time response of a system, you always consider second order system, because only 2 poles will be dominating. So if you know the time response of a second order system where you are considering the 2 dominant poles to find the time response, that is enough in the first level of control systems to know the time response of a system. So time response of a system, I will find it for second order system even if the order of the system is more than 2. If it is first order system, then I cannot use second order system. So then I'll be choosing first order system. If it is third order system, I will consider the 2 dominant poles of that third order system and find the time response. So what I'm trying to say here is, when you are finding the time response of a system, you try to identify 2 dominant poles and you consider those 2 dominant poles as the second order system and find the response of the system. So that's why in control systems, we always talk about time response of second order system only. We will not consider time response of third order, fourth order, fifth order, because all these highest orders will be converted to will be seen as 2 dominant poles will there. So you consider those 2 dominant pole positions and then try to apply the rule of time response to find the time response system. Then you can easily find the time response of such a high order system by considering only the response of these dominant poles. Hope okay you can able to understand okay what is this dominant pole is. So dominant poles are one which are closer to the imaginary axis, which are closer. Why you are talking about only closer to the matched axis? Because the one which is there closer to the matched axis will totally dominate the system response. The one which is far away from the matched axis will have a fast decaying response. Their response will not be too much considered for finding the stability of the system. So they will not be contributing too much to the time response of the system. Okay. Okay, I'll come to this frequency response bit maybe in the coming classes. Let me just show you this. What is that? 20 sim. I won't show. I want to just. Where is that? 20 sim is here. Okay, let me just show you some. How does that poles and zeros will look like? All those stuff I'll just show you. I'll show you that frequency response, time response, and when you apply some. Okay, it will take some time. Okay, fine. Okay, this is the window where you can do the just have a look at it. So I'll go to insert. I will insert a submodel which is a linear system. Just to look at that system. This is a open source. You may have to just give your email ID, all those stuff. See now I'm inserting a submodel. In that submodel it's a linear system. Now this is what the linear system is. Now you can see I can define the system using these four different ways: state space, transfer function, zeros and poles, and gain, and of course eigenfrequencies. So let us go for this poles and zeros as the way how I enter the system transfer function. Let me say edit. So shall we have let me delete these two. Shall we have this? So what I'll do is I will define a pole at s. Let me just show you what I want to. I want to show you this 1000 by s plus 1000. Correct? Let me just do this. So how do I do this? So this is in which form? This is in, because it is s plus 1000. This is in pole zero form, and this gain is, that gain is what? Root locus gain. If you can remember the earlier class, this is my transfer function. This is my transfer function. I can write it as k by s plus p1. So what is k here? K is root locus gain and p is the pole position. Where is the pole? Pole is at minus 1000. Correct? So let me edit this way. So how do I edit that? See here, this is my pole. So where is the pole? So I'm going to add a pole which is at minus. Okay, this should be minus 1000. You can see I'm adding the pole. So there is a pole added at so and so. Now let me make, can you see the root locus gain? Let me make the root locus gain as 1000. So this is my root locus gain. The moment I make the root locus gain as 1000, can you see the system gain? System gain is 1. How did you get this system gain as 1? Let me just go back here. Let me go back here. Can I write this as 1000? I'll take out 1000 outside. Is it not okay? 1 plus s by 1000. This will go. Is it not 1 over 1 plus 0.01 s? 0.1, 0.01, maybe 0.001. Correct? So what is this here? What was k? What was this 1000? That was root locus gain. So what is this one? System gain, because you have divided this by this. So this is system gain, this is root locus gain, and this is your, where is the pole position? Pole position is minus of 1 over 0.001, which is nothing but minus 1000. Minus 1000. So my pole is at minus 1000. Exactly this. See here. I'll apply, say okay. See where is this pole zero plot. See here. See this. This is at minus 1000. You have a pole at minus 1000. You have a pole at minus 1000. Correct? This is in S plane. In S plane, I have a pole at minus 1000. Is it clear? So let me just tell you again. So here we have took this pole 0 gain. We want to edit. So whatever is there, you delete all the available by default one. Next you start adding. Where you want to have the pole should be at minus 1000. So pole is at minus 1000. You add that, and of course the only one is required. You can see root locus gain I have edited as 1000. It has become so. Then you say apply this and OK. Now we can know where the pole 0 is. So this is a pole 0 at minus 1000. Now can I add one more pole now? What I'll do, I will just go back here and I'll add. So this is what? So this is 1000 by S plus 1000, and let me add S plus 200. So my root locus gain, let it be 1000. This is this. So what is the expected system gain? System gain is now you take out 1000 outside, 200 outside, it is there. So then this will go. What is 1 over 200? 1 over 2 is, so 1 over 200 is point not. Just a minute. So 200 inverse is 5 minutes. Sorry, point not 5. Point not 5 will be the system gain. So let me just check out whether that will be true or not. Come back here to this. Let me edit. What you are adding? You are adding one more pole. Where is the pole expected, or you want to have it to be at minus? Okay, I will apply. You can see there is a pole at this. See now the root locus gain we won't have it as 1000. Can you see the system gain has become point not 5, which is that we have written here, point not 5. Now if I just apply and say OK, and you see where poles and zeros. See now there is a pole at minus 200, there is a pole at minus 1000. Now let me add a 0. Shall I add a 0? I will add a 0. Where you want to add a 0? Let me have S plus 300. S plus 300. So now I'll add a 0 at minus 300. I'll apply. Now what I'll do, so this is 300. So there is a 300 coming here. What is 300 into 0.005? This will become 300. Is it not into 300? Is it not 1.5? Can you see the system gain has become immediately 1.5 when I added this? So this is apply. Okay. See where is pole 0 plot? Can you see? There is a 0 with indication, with a representation as a circle which is there now. Correct? This is what is the location of all these poles. Now this is okay. What is that I'm trying to enter is they're all open loop poles. Now we know that where does the poles will go. So maybe in the last class we are talking about, no? So this pole will go here and this pole will go this side. So that you can immediately see here in this by plotting root locus. See here. Let me just, this is the value of k. This is the value of k. Now you see here. So now let me just go back here. Now assume that I have something like this. So it is k into S plus 300 by S plus 1000 and S plus 200. Correct? This is k now. So where are your open loop poles and zeros? So this is at minus 200. This is at minus 1000, and there is a 0 at minus 300. Now at k is equal to 0, the pole is here. That's what you can see here. I'll show you. You can see this is k value. See now, this is your linear system. K is 0. See here, this is my pole, this is my pole. The moment I start increasing, just have a look at this arrow mark, and can you see there is a dot coming here? Can you see there is a dot coming out here? And can you see this pole is here? This is started moving. The moment when I start keep increasing, can you see this is keep moving? Let me change this axis to maybe x-axis. Let me make it maybe this another 0. I'll make it so that you can make out that. Fine. See now, this is okay. That is too much. Or let me make it okay, x-axis. Let me simply make it 2000 is enough. Okay, fine. See now, this has moved here, this has came out of this. Now when you start moving, see now, has this come closer to this? Has this gone here? So now, okay, I will show you better. Suppose if the value is a bit lesser, so I will just go back and try to, I will just change this number. That is too much. So what I'll do is I will make this as maybe minus 10. This is I'll make this minus 10. Let me make this at minus 2. Okay, this is apply, and then 0. Let me make it at minus 3. Apply, and you make a system gain as simply 1. Let me make it 1. Okay, let me apply this. Okay, now let me just apply. Okay, I just reduced it so that you can comfortably see it. Okay, fine. Now let me do the root locus. See now I'm just keep moving. See here, and I'm keep moving. Has this come here? Has this come here? If I further increase, just have a look at this k value. When k is 5.1, this pole has moved here. How about this pole? This has moved here. If the value of k becomes larger and larger, where does this will go? This will go in search of its destination, which is there at infinity. Where is the destination of this? Its destination is here only. So as the value of k increases larger and larger, this is keep moving out. Can you see this will going to move outside, whereas you can see this will be there reaching. So this is almost at the, can you see it is minus 2.9999. This is not yet become minus 3. This actual location is minus 3, but it is still not yet reached because this is still not at 1000, sorry, infinity. So now what does this will actually say is how does the poles will move if it goes something like this. Now what we can do is, let me put a pole on the complex. So how do you make it complex? I'll just edit this. So this is so and so. Let me make some imaginary value also, something like this 3. I will apply this. See now, do you have poles and zeros here? Let me just take out this root locus. Can you have, there is a pole here, there is a 0 here, there are 2 poles here, there are 2 poles here. So where does this pole will go? This will go here as k increases. Where does these 2 poles will go? These 2 poles will go to infinity because their partner is there at infinity. So that's what is there, this root locus says. This root locus says if you increase the value of k, see now, as you are increasing the value of k, can you see the poles are coming out? Can you see this arrow mark is moving out here? See here, this dot is coming out, this dot has come out, this arrow has moved there. If you keep increasing, they will actually move. Can you see, this is coming closer to this. So as k is infinity, it will sit here, but this will go to infinity, that will also go to infinity. That's what is the movement of closed loop poles as the gain changes. Suppose if you add one more 0 here, Suppose if I add S0 at -4, what happens? The shape totally changes. See here, the moment I add S0 at, if I add S0 at, if I add S0 at -4, you can see it's a totally different ball game. See now, if I just see the root locus, see now, it's not going to infinity here, but it is, one is going here, other one is going here, other one is going to infinity. See now, it's beauty to see how does the poles are moving. Can you see the dots? Can you see the dots now? See now here. Okay, I can show you the dots. Can see now? This is how the dots are moving. Can you see? Can you see this? It's beautiful to see how does this dot is coming to this, how does this arrow is coming and reaching there, and how does this dot is moving out. Let me just go back here. See here, this is a lower value of k. This is increased. You can see they came here and this is started deviating. See now, see now, see now here. So this has reached, this has reached almost -3. You can see it's almost at -3. This is almost reached at -4. This is slightly away from 4. This is slightly away from 3 because this k has not yet become infinity. But this is still going towards infinity. This is the whole idea of control system, is how does this closed loop poles will take their journey towards the zero. The addition of 0 will totally change the pole movement. The poles were moving outside to infinity, now they are coming and settling in 0, and there is a 0 which is there at infinity. So of course, let me show you one time response of this. So maybe of course in this particular case they are applying a step input. Let me show you for a system which is let me just take out this. So let me take out this also. This is a first order system. For a first order system, if you apply a step input, how it looks. Can you see this is your step input? You can see this is how the response is. The response of the system is something like this. Suppose if I add one more system, one more pole, if I add one more pole at -6, what happens? -6. Okay, now what happens to that? So apply. Okay, if you do the step response, it is something like this. It is something like this. Suppose if you have a larger gain, make it as a larger gain. See what is the response of the system. This is so and so. Suppose if I have a poles and zeros at different location. Now what I'll do, I will edit, I will just delete this, and I'll have a complex pole at some. Okay, this is this. Now I will apply. You can see I have something like this. So now there is an overshoot. This is a second order system. This is a second order system. Of course, in control systems, we deal so much about what is the response of the system for. Suppose if I make this, maybe let me show you this. Suppose if I make this value bit. Okay, now see, this is the overshoot has increased. In the previous case there was a small overshoot, now it is. Now you will spend a lot of time in trying to understand what is the overshoot, what is the settling time, what is the rise time. So there is a lot of exercises you'll be doing for a given system with poles at so and so position. What is the step response of the system? One of the unit deals completely about this response. We can actually predict the response, how much will be the overshoot, what will be the time, what will be the settling time, what will be the rise time for a given transfer function. So these are all the stuffs which is there in the time response of the system, which you can visualize very effectively using this 20sim simulator. So this is very handy. And of course, when it comes to frequency response, we will use this Bode plots very effectively. We'll use this Bode plot. Of course, we will learn all these things as semester begins and rolls down. So you will certainly enjoy the control system classes. Only thing is that you have to slightly hang on to the things, know some very basic mathematical what equation simplifications, and if you are all there, good. So then nobody can stop you in learning control systems. So thank you so much for being with me for last 3 days. So hope to meet you in regular classes for my ET students. For others, when it time comes, okay, we'll certainly meet online. Or of course, you are most welcome to meet me at any time. Thank you so much.